Hi everyone! In this video we're going to learn about a special coefficient, it's called coefficient of determination, that measures how well a linear model describes the relation between the explanatory variable and response variable. So to better understand the idea behind the coefficient of determination, let's continue with our example where we have a bivariate data describing ages and prices of certain Honda Accords, and let's answer the following questions. So the first question is, how can we predict the price of a randomly selected Honda Accord? Notice the words randomly selected. It means that we're not concerned about age of that car. Well, to estimate or predict the price of a random Honda Accord, knowing this information is by computing the average price, or we say the mean price. So let's try this. Since we're going to be computing the mean of the response variable, we're going to denote it by y bar. And remember, to compute the mean, we have to add up all the values. So it's 13 plus 9.2 plus 7 and so on and so forth. And we're going to add and we're going to divide by how many values we added up. So we have 8 here. So divide by 8. That's 11.66, and then of course it's $1,000. So the average price for a Honda Accord is $11,660 based on this data set, and that would be our prediction for a randomly selected Honda Accord. But now suppose that this particular Honda Accord is 3 years old, so we have now additional information, right? Now it's not a random, but we also know its age. And we know that there's a linear association between age and price. We already showed that in a previous exercise. And that means that knowing the age, we can improve our estimate by using the least squares regression line, or the regression equation. This is how the regression equation looks like for this data. Again, we found it in our previous exercise. So to estimate the price of a 3-year-old Honda Accord, what we do, we plug in 3, the age of the car, for x, that's the explanatory variable. In other words, it's going to be y hat. Oh, and yes, by the way, the predicted value of the response variable we denote by y hat. So it's negative 0.9 times 3 plus 18.4. That's $15,700. And now we have another prediction estimation, and it's based on the given age. And we know if we pick different age of a car, then the estimated price will be different. So while the average price stays always the same, the linear model allows us to see the difference or change in the price depending on the age of a car. So in statistics, we say that some of the variation in price or change in price is explained by the linear relation between age and price. And we're going to try to show this graphically. So on this picture, I have the scatter diagram describing the given bivariate data, and we also have a linear model that we use to make the prediction. So first of all, I'd like to indicate where the mean average price for this situation. So we computed the mean average price to be 11.66. So it's going to be about over here, 11.66. And I'm going to draw a horizontal line here. So the average, or the mean price, always stays the same no matter what car we randomly selected for estimation. And if we focus on a 3-year-old car, then there are going to be 3 specific values of the price associated with it. So first will be the estimated price based on the mean, which, as we said, always stays the same. So let's consider this point. Second, the estimated price based on the linear model, that's going to be this point on the line, right? That corresponds to 3, age 3, right here. And then one more value, and what is that? Well, that's the observed value. So that's the value from the table, because in the table we did observe the actual price for the actual 3-year-old car, right? 17,000. So that's where it is on the graph. And now let's compare those values, or let's note their differences. So if I look at this distance, that distance between the mean price and the predicted price is going to be difference y hat, predicted price, minus y bar, the mean price. And that's going to be difference explained by car age, because remember, mean price or average price does not consider age, but using linear model allowed us to use age to make estimations. So that difference, that improved estimation, is explained by car age. Difference explained by car age. Okay, so that's the first difference. And then the second difference that we're going to look at will be between the observed value and the estimated value. So while we improved our estimation by using linear model and considering age of the car, we still didn't get the same price as it was observed. So this resulted in underestimation. Well, the reason for that is because age is not the only factor that influences the price of the car, right? It can be condition of the car, it may be color of the car, and things like that. So that means that there is always possibility for the difference, and that's difference between the observed value and estimated value, that's not explained or unexplained by car age. Difference unexplained by car age. So one more time, while a linear model shows change in the price of a car based on its age, age is not going to be the only factor that influences the change in price. So higher the coefficient of determination is, better the least squares regression line describes the relationship between the explanatory and response variable. So let's summarize what we've learned so far about the coefficient of determination and learn some other important facts about it. The coefficient of determination is denoted by r squared. In some sources you'll see a lowercase r, and in some sources you'll see uppercase r squared. And as we said, it measures the proportion of total variation in the response variable that is explained by the least squares regression line. So overall, what you need to know is that, simply said, it measures how well the least squares regression line describes the relation between the explanatory and response variables. What else we need to know about it? So first of all, the coefficient of determination is always expressed by a number between 0 and 1 inclusive, meaning that it can be 0 and 1 as well. And we use percentage to describe it. So that number, that decimal between 0 and 1, we convert to percentage when we write interpretation. Now, the closer r is to 1, or 100% in terms of percentage, the better the line describes how changes in explanatory variable affect the value of the response variable. And this is how we find it. So we're going to be using the simplified way of finding, which is very easy. We simply square the linear correlation coefficient. And let's try it for our example. In previous exercise, we already computed the correlation coefficient for our bivariate data, describing the age and price of some Honda Accords, and we know it's negative 0.874. So that means that the coefficient of determination, I'll use both notations here, is the square of that number. And that is 0.764. So it is between 0 and 1. And as it says here, we use percentage to describe it. So 0.764 we convert to percentage. and that is 76.4%. So this is going to be our conclusion. 76.4% of the variability in price can be explained by the least squares regression line. In other words, while linear model shows the relationship between age of the car and price, as age changes, the price changes. Age is not the only factor that influences the price. That's why we see only 76.4%. There are other factors that would affect the price and its change. And finally, let's just look at a few more examples where we have scatter plots and we have linear models shown, as well as the corresponding values of the coefficient of determination. So on the first picture, we can see exact linear association where all points lie on a line. And in this case, 99.99%, almost 100% of the variability in Y can be explained by the least squares regression line. So there are no other factors that affect the variability in the response variables. This model is perfect, and we're able to use it to estimate the values of the response variable accurately. Next picture shows a strong linear model. Points come very close to that line, and for data set B, 94.7, so that's a high percentage of the variability in Y can be explained by the least squares regression line. And let's compare that with the last example, where while we see the linear model, points are pretty far away from it. So based on this model and the least squares regression line, it's been determined that only 9.4%, so that's considered to be a low percentage of the variability in Y can be explained by the least squares regression line. So it means there are many other factors that would influence the change in Y. So linear model is not that effective at all in this case to make predictions and estimations.